All right, so we're gonna fill out this energy notes worksheet. I'm gonna start off by talking a little bit about work in terms of a single object. So let's say we've got a block right here and it's being pulled by somebody, so T for tension. And if I said, okay, draw a free body diagram of the block, then we would have the gravitational force going down, and then we would have the normal force going up, and then we'd have the tension force going to the side. Now, one equation that we're going to use in this worksheet is work equals F parallel multiplied by D. So the key is that force is a vector and displacement is also a vector, and the force needs to be in the same direction as the displacement. So if I said, well, what's the direction of the displacement of the block? The answer would be to the right. So the displacement, it could be measured. Let's say it gets dragged a certain distance. And, I'm going to take off that last one, showing because displacement is a vector, so it gets dragged to the right. So we'll call that the positive direction. So that was positive displacement. And we would only consider work to be done, right? Work is done only if the force is parallel to the displacement. So, right? So if the displacement is going to the right, or I should say in the x direction, then we only care about the force is going in the x direction, which is the tension force. In this example, the gravity is going down and normal force is going up. Those forces are perpendicular to the direction of motion. So it's very important that we only consider forces that are parallel to the direction of the displacement. So keep that in mind. So let's go and start filling out this worksheet. So just some symbols. So work is W, energy is E, change energy will be delta E, and F parallel can be rewritten with this little symbol right there. All right, two parallel little lines. Okay, in terms of equations, right, we have, again, work equals F parallel times displacement. Okay, and we have delta E, change in energy, equals energy final minus energy initial. Okay, and then if an object has energy, right, then it has motion. So that's called kinetic energy, and the formula is 1/2 times the mass of the object times the velocity of the object squared. And the units, right, for energy are joules, and the units for work are joules as well. Okay, and that would be capital J. So just keep that in mind, that the unit for energy and work is joules. All right, and finally, one last equation is the work of an object is equal to its change in kinetic energy. Okay, so if you speed up an object, then something is doing positive work on it. If you slow down an object, something is doing negative work on it. Okay, so let's take a look at this situation. It says a 10 kilogram object is released from rest near the surface of the earth and falls 2 meters. Well, if it's released from rest, then it's falling through the air, and the only force on it would be the force of gravity. And that's it. And that drawing, that free body diagram, would not change as it falls. The force of gravity doesn't change near the surface of the earth. So it only would change if you move far away from the earth. Not like 1,000 meters, but like thousands of kilometers. Then G would start to noticeably change. But if it falls a few feet, FG doesn't change, right? And don't forget, we can calculate FG from mass times G, where G is approximately 10 newtons per kilogram. and mass is measured in kilograms. Okay, so when in this sheet right here, we are talking about a single object. So we're talking about the energy of a single object, not the energy of a system. So this is the most simplified way to look at energy, is just say, hey, let's look at this object, and is it moving or not moving? If it's moving, it's got energy. If it's not moving, it does not have energy. Okay, so it says calculate the work done on this 10 kilogram object that falls 2 meters after being released from rest. So it says calculate the work done. Well, according to physics definition, we need F parallel times D. So let's draw the situation. So we've got this object, and then it's going to fall, right, 2 meters. It's going to end up right here. So that's our displacement, 2 meters. Now, since we're moving downward, I would just go ahead and call downward the positive direction. So our displacement is positive 2 meters. Now, again, the formula is work equals F parallel times D. Well, do we have a force in the downward direction? Well, we do. There it is. It's gravity. That is the force that causes the displacement. So here we go. So work equals force parallel times D, because the question is asking for the work done. So that's our guiding equation, right? And the force, the parallel force, is Fg. So we can replace, right? We can replace F parallel with Fg, and then we can replace Fg with mg. There we go. So just a little substitution. And now we can actually calculate it. We can say the work done by gravity on this object is the mass, 10 kilograms, times g, which is 10 newtons per kilogram, times the displacement, 2 meters. All right, and if you follow the units, we get Newton meters, and 1 Newton meter is equal to 1 joule. So we get 100 times 2 is 200 Newton meters, and that's the same thing as 200 joules. So that's our answer right there. So work equals 200 joules. Sorry, it's a little sloppy. All right. Now, the next question says, what is the change in energy of the 10 kilogram object? Well, let's come over here for a second. What is our object, right? We're not even dealing with systems yet. That'll be the next day. So our object is the block. Did I call it a block? 10 kilogram object. It's not even defined what is. It's probably just a block, but we'll just call it object. The external forces are Fg, all right? The initial system energy is 0. And the reason why is because it was released from rest. And if you calculate 1/2 mv squared, the velocity would be 0. So you have no initial energy. The final system energy, right, will be calculated from 1/2 mv squared. We don't know exactly how fast it's going, but this expression would tell us the final kinetic energy of the block, okay? So the change in energy. So the change in energy, right, delta E equals E final minus E initial. That's our equation, right? And the final energy, right, is equal to, well, I don't think I explained that very well. The change in energy, well, work is equal to the change in kinetic energy. So when we say, how can this help us, right? Well, that means that work is equal to the final kinetic energy minus the initial, the initial kinetic energy, right? And we know how much work was done. It was 200 joules, That was the work done by gravity. We don't know the final kinetic energy, but we do know the initial kinetic energy was 0, right? Because when we use this equation and replace velocity with 0, this whole expression goes to 0, right? 1/2 times m times 0 squared would give you 0. So you were left with a final kinetic energy of 200 joules. Okay? So the change in energy was equal to the work done on the object, which is 200 joules. So not only is this the final kinetic energy, this is also the change in energy, the difference between the amount of energy from when it started to when it ended. All right, now if we want the final velocity, right, what it actually was, right, we would say, okay, kinetic energy equals 1/2 mv squared. Right, we're looking for the final velocity v. We know that 200 joules of energy was our final energy. We know the mass is 10 kilograms. We don't know v. So that's the physics. Now we just have to do some math. I'm going to multiply each side by 2, right? Because 2 times 1/2 is equal to 1. That's why I chose the 2, because it's the reciprocal of 1/2. So I end up with 10 v squared equals 400. Then I divide each side by 10. And then I would get v squared equals 40. And then I would take the square root of each side to get v equals the square root of 40. Now, I don't have a calculator, but it's around 6 point something. Or if you want a little math review, that's the same thing as the square root of 10. No. What number squares easily? Yeah, square root of 10 times the square root of 4. 2 radical 10. So I don't know what that answer is. There's your math answer, but you would just plug in your calculator square root of 40, and that would be your answer in meters per second. So don't forget to add your units, because we're talking about velocity.